My wife is prettier than I am. This talk has had many titles in the past, or different variants of this talk. It's been called the Science of Perl, the Art of Perl, the Science of Art, Science of Science, the Art of Art, the Perl Perl. Anyway, they don't pick what studies in the ballistic arts. Now, I would first like to define the ballistic sciences. You know what the ballistic sciences are, especially those of you who are into that kind of engineering. Ballistic science is like shot put, catapults, artillery, ICBMs, space probes. I used to work at JPL, so I know about space probes. Putting the man on the moon, that's a ballistic science. Now, ballistic arts are just a little bit different. They're more general. Now, those are things like basketball. You know, basketball, you shoot it and it goes through the swoosh, switch to the net, and you say, I can do that again. And then you throw an air ball. It's hard to reproduce. So those are ballistic arts. Things that are not quite so scientific. Baseball, cricket. Come on. Football, American football. Bowling, curling. Golf is a ballistic art. Golf is one of the harder ballistic arts because there are several removes from the control. Because you have to start off, and so you do this, and then you're moving your hips in order to move your shoulders, in order to move your hands, move the other end of the club, which you hope hits the ball, and if you're really lucky, the ball gets closer to the hole. So you're throwing many things. Ballistics means throw. It's a Greek word. Putting a golfer on the moon, that's a ballistic art. Putting a cricketer on the moon might even be harder, but I bet you're going to do it someday. Now, let's go and generalize it one step further. Make it a little more metaphorical. What's a ballistic liberal arts? Computer programming, things that you're trying things and they may or may not succeed. Design and architecture, sometimes things stand up, sometimes they fall down. The scientific method in general, management, delegation, writing, trying to get someone to understand what you are writing or saying. Raising kids, there's no guarantees there. You try your best and they turn out however they're going to turn out. I got 4 kids, so does my wife. a dicey subject. Designing Perl. You try something, and sometimes it works, sometimes it doesn't. Or in the case of Perl 6, designing Perl again. And we'll talk about that. And basically, pretty much everything that you want to do, there's no guarantees that it's going to turn out the way you expect. So those are all, everything you do is pretty much a ballistic liberal art. Now, I often show this picture about how Perl was initially designed back in 1987. How many of you were born after 1987? I feel old. Perl was sort of an unusual language, computer language, because I didn't come entirely from a math background or a computer science background. They didn't really even have computer science curriculum back then. It sort of did. But, so Perl, I was trained as a linguist more than a computer person. So I studied various human languages, and that had a great influence on Perl. And computer science had some influence, and art, and common sense. Now, don't take this diagram to mean that linguistics is the opposite of computer science, the opposite of common sense. Although I have had some computer science professors who said that there should be no art involved. It should be pure science. Well, then why did Don Knuth call his book The Art of Computer Programming? This talk could have been called The Linguistics of Perl or The Common Sense of Perl. But really, Perl draws from a lot of things. It's buzzing or green. I'll use it later. Okay, does this mic on? I'll put this one far away so we don't hear multitasking. Okay. Ecology. Perl has drawn its design from many things: mathematics, sociology, psychology. Or is the buzzing sound system? Wow. And chemistry, and physics, and some of the soft sciences, anthropology, all. But what is science? When we say science, is it just sitting there and figuring out? Is it just reading a book and somebody telling you what's going on? Well, that's what the Greeks sort of thought. They thought if you just sat there and thought, you could figure everything out. And that doesn't work very well. Deep science works much better. You actually try things and blow them up. It's experimental, and sometimes you succeed. But Make magazine, I love this. If any of you have ever read Make magazine, they have this slogan. Void your warranty, violate your agreement, try a circuit, blow a fuse, poke an eye out. That's how you get things done. You try things. Were any of you in the junkyard wars last night? And so sometimes you succeed, but you also fail. And sometimes you just fail. Sometimes you win what we call a Darwin Award. Those are awarded every year to people who take themselves out of the gene pool before they reproduce. I am no longer eligible for a Darwin Award because I have reproduced. So we've got ideas from biology and physiology. Physiology is rated R for nudity. We get ideas from genetics. That's rated R for sex. We get ideas from how things evolve over time, which is, of course, rated R for violence. Have you ever heard of the Harvard Law? The Harvard Law says that under controlled conditions of food, water, temperature, pressure, humidity, and so on, the organism will do as it damn well pleases. Biologists or something, which is of course rated R for profanity. But and paleontology is sort of a biological science. I dug up this fossil way back when, and it's sort of shaped like an egg. This is how things looked. If you were a Unix programmer in 1987, you had two choices, well, one choice. You could either program in C or you could program in shell. And obviously they had to be opposite ends of the spectrum, and they were good for different things, so they, there was just this one continuum. The big revelation back then was that there was actually two different dimensions. It sort of opened up as like a clamshell. I realized that C was good at something and shell was good at something else, but they were independent of each other. Orthogonal is the word computer scientists have to use. And so I named what C is good at is something like manipulexity. No, you probably haven't heard that word before. And what shell is good at is whipuptitude. You can whip things up a little bit. And so that I realized if you graph it like this, there's this whole area where neither C nor shell are good at. Since C is not good at whipuptitude and shell is not good at manipulexity. So Perl was born, the ideal Perl, kind of egg there. And that's Perl 1. It sort of started moving into this ecological niche in biological science. There's a new continent. We discovered a new continent, and we're an organism moving into it. And so it grew, because there wasn't much competition back then. And it continued to evolve and evolve. And now we have a Perl book with a camel on the cover. We got to Perl 5, which we are still using heavily in the world today. It had a module systems, extensible beginnings of object-oriented system, and you could do functional programming in it. Though none of those things were as easy as they could be. So we had 5 successful organisms. Why? This talk is about the history of Perl and the future. So why was Perl 5 or 1 through 5 successful? Was it near hybrid rigor because we took ideas from all these different languages? Hybrid rigor is the polite term. The not so polite term is but there are many reasons why Perl succeeded. Evolutionary, psychological, linguistic, anthropological. If you're going to pull stuff from all over the place, then you have lots of reasons. And sometimes there's no good reasons. I'm not... human beings are not rational, they're merely rationalizing creatures, by and large. So I have a set of irrational ideas that, I don't necessarily have a good reason, but I just believe them. I don't like indented syntax that just sort of hangs there. I believe that most people don't actually like abstraction very much. Now, if you're a mathematician, you love abstraction, and you keep defining layers of abstraction. But most people don't seem to like abstraction very much. They like concrete programming. I have to believe contradictory things. A language can be simultaneously wonderful and awful. That's both human languages and computer languages. I have to believe that ugly things can be beautiful and beautiful can be ugly. My best example of this is the Lisp programming language, which a lot of people think is the most beautiful language ever created. And yet, every program that's written in Lisp is ugly. How does that work? I believe that visual metaphors are important. What do I need there? I'm sure. not only is the indentation that you do a visual metaphor of how deeply nested you are, but you ought to be able to lay out your code such that things look like what they're functioning as. Now, here in this program, we've laid out this set of list here, right here. And we're actually doing a cellular automaton. These are our 8 directions from our cell. You can lay them out like this, and it's important to be able to do things like that to clarify what you're doing. Lower level visual metaphors. Words should kind of look like what they're doing, so we try to make sure that the words and the symbols play well visually. As a language designer, I have to simultaneously care what you think and I have to not care what you think, because you think a lot of different things. But some of what you think is right. Finally, I believe that whatever name you use for him, the creator of the universe had free will and chose to create us, and therefore created us to be creative too. And programmers should be able to make choices. Not just for good and bad, but for arbitrary choices, because then you can be artistically creative. However, those were my irrationalities. Other computer language designers have their own irrationalities. When I was young, this was popular. You could build anything with NAND gates. And that usually came from the mouth of somebody coming from an electrical engineer who thought he was a language designer. You need to start over. Who says that? Well, APL. Everything is different. We don't need to start over. C++. Most of the problems with C++ stem from having been derived from C. We need to start over. Java. We don't need to start over. We'll just pretend we did. This is a 4th generation language. Who cares about bits? Well, the 4GL language designers thought that, and that's why we don't have any 4GL languages out there anymore. If we put in English phrases, that makes it readable. COBOL. Text processing doesn't matter much. Fortran. Everything is a string. Snowball. Pickle. Simple languages produce simple solutions. Oh, this is a subtle one. People actually believe this. But think about C. It's a simple language. Are the solutions in C simple? No. If I wanted it fast, I'd write it in C. This is almost a direct quote from the first manual page for the awk programming language. I thought of a way to do it, so it must be right. I thought of another way to do it, so it must be right too. People care about elements. Specification is good enough. Abstraction is usability. The common kernel should be as small as possible. You know what happens when you do that? You get a little fourth kernel, and then everyone has their own system on top of it. Most programs are designed top-down. That's how. Let's make this easy for the computer. And hard for the programmer. Everything is a list. Everything is a function. Basically all your functional programming languages. Everything is a vector. APL. Everything is a hypothesis. Everything is an object. Ruby. Any Ruby programmers? There's a lot of Perl in Ruby. And there's some Ruby in Perl 6 too, so I'm focused on that. Programming Programmers should never have been given free will. This is obviously something that we don't believe. Programmers should be forced to use their free will. That's Perl 5. There's so many choices, you have to make a choice. The problem with Perl 5 is actually that it doesn't have good defaults, and that's something we try to cure in Perl 6. So, what about psychology? Well, I believe that if your computer language has a lot of theory in it, and you force people to learn that theory, people won't like your language. So you say it like this, or you just say, hide the fancy stuff. It's okay if the computer language has fancy stuff. Perl 5 has real closures, you can do real functional programming, but we sort of hide it from people. Linguistics comes into it. Perl behaves kind of like a natural language, and that's why it works. With a natural language, if you're learning a second language, you learn it as you go, or even your first language. You learn it as you grow up. You only have to learn the language once, and though I suppose the exception is Haskell. I've learned Haskell several times now. But your native language, you only learn it once, and you use it often. So we optimize not for how easy it is to learn, but for how expressive it is. There are many acceptable levels of competence. You do not expect somebody who's 5 years old to talk the same way that a 50-year-old talks. There's more than one way to do it. That's the Perl slogan. You get choices. In natural language, if you want someone to say it differently, you say, could you rephrase that, please? And you can, because natural languages give you multiple ways to say it. There's more than one way to do it. There's no shame in borrowing words, unless you're French. Languages have a fractal dimensionality. It's like getting from here to there. When I came, I rode in a car, and from there I rode in an airplane to Chicago, and from Chicago to Delhi to Kolkata, and then I rode a car. Well, there was a bus there at the airport too. So it's when you're saying something, you sort of rough it in, like the big plane rides, and then you have little transportations that refine what you're saying. There's little orthogonality in natural language, and many shortcuts. It's okay to be ambiguous as long as it's easily resolved. And we use verbal punctuation. We put in pauses. We do things with our voices to emphasize things. It's kind of punctuation that we also have in written communication. And we use various concepts from natural language, like numbers and case and word order, which is important in English. It's not so important in Greek. Pronouns are important in natural language. We have those in topics. In fact, we have a pronoun for the topic. It's called $_ in Perl. And discourse structure, which means linguistics larger than a sentence, large chunks of text. So if you're familiar with fairy tales, you know they always have to start out once upon a time and have to end there happily ever after. There's this frame. That's part of the discourse structure that you have to follow. You need to put yourself. There's not much theory in natural language, not much style. And the design of natural language is kind of distributed. It's not just one person designing it. And languages diverge over time, and sometimes they converge. You get several languages that form a Creole. English is a Creole language. It's composed of Anglo-Saxon, Viking, and French, and who knows what. Japanese is another Creole language. Language without culture is kind of useless. It's basically dead. We call Latin a dead language because nobody actually speaks Latin as their native tongue. So because of that, I also have this sort of anthropology notion that the culture is actually just as important as the language design itself, because it's the people the culture who do the design. I should sort of help. So in fact, it's even more important to have people. We try to be accepting of newcomers, and we allow people to form sub-tribes to do databases or this or that or the other thing. That's okay. That's all culturally acceptable. It's a culture of sharing ideas, of capturing knowledge, and that's why we have the CPAN repository of cooperating, and most of all, it's this culture of where we optimize for fun. That's why I give the talks. Now, when I was starting off, this was the accepted design paradigm. It's called the waterfall chart. Perl was actually started in the defense industry, and you always wrote your specification, and you did your design, and you did your coding, and you did your testing. Well, we don't tend to think that way anymore. Modern design is more of a whirlpool, and there's feedback. I mean, you do your testing, and that feedback feeds back to how you're coding. That also, those two feed back to your design, and that feeds back to your specification. In fact, agile programming tends to even do test-driven design. So you revert the whole thing, write your test first. And when you're done writing your test, you can do your coding. And once you're done coding, you can do the design. And once you have the design, the specification is pretty easy. But you might think, well, but not everything is ballistic. This is about ballistics, trying to throw things out there and send things down those arrows and see if they work. Well, but an airplane, that's not ballistic, right? You're controlling it. Well, or a butterfly is also like a jet plane, only smaller. The thing is, there's these feedback loops, and every one of those feedback loops is, in the sense of a ballistic, there's a delay line there. So you still have to predict what's going to happen on every scale. It's like a strange attractor that way. So everything on some scale or other is ballistic. So when you're done doing this design, well, it's iterative, and maybe you never design. But you're familiar with the potential energy curve and the ball rolling on it, finding the low spot. If you're an economist, you do hill climbing algorithms, and you should just invert this, and then the ball rolls uphill. I don't know how that works. On the other hand, computer science, the trees grow down, so go figure. So the ball rolls and tries to find the optimal location. So are we optimal here? It seems like it, but you could be in a false minimum. And you just think you're happy. And exploration is energy. So you either have to climb over that hill, and that's hard, or you have to do quantum tunneling. That was big. But how did we get there? We call it the process. Okay. The industry phrase for this is plan to throw one away. The prototyping thing. If you're in this sort of situation, then it's good to write the first thing, knowing that you're going to switch over to the second. And throwing things out, throwing ballistics. 10 years ago, we decided Perl really needed to be redesigned. And we decided it was time to break things. That would be a community rewrite. So we asked for suggestions as to what we should break and break backward compatibility. I expected about 20 suggestions, RFCs. We got 361. That was surprising. 361 is much greater than 20 for you mathematicians. So I discovered the first law of language redesign is that everyone wants the colon character. The second law is I get to decide what the colon character is. But redesign is easy. You just throw out everything bad and keep the good stuff. We looked at those 361. It took me about 6 months just to recover from the shock that people were having that much problem with Perl 5. But we looked at it and we said, you know what? we're just going to take the time to do this right the first time, or the second time, depending on look at it. And we escaped the second system syndrome problem by just taking long enough to do it. So we have the twin goals of simplifying things that were too complex and making things more powerful. And at the same time, we ended up with better object-oriented programming, better functional programming logic, better parallel programming. What do we want there? It's also extensible, so you should be able to add more paradigms. So lots of buzzword compatibility, scalability, extensibility, we hope. So we have some meta goals. This is more or less summing up again what I said earlier. A meta goal. This is the idea that this is an organism, and the organisms that will succeed that in the future are there are two kinds of ways of succeeding in biology. One, you can be a specialist in an ecological niche, and some computer languages do that. But Perl is a generalist. It's like a crow or a raven or your typical that kind of bird that just can live anywhere. So we want to be able to evolve over time into what language we want over the next period of time. So we don't even know what Perl 6 is going to turn into. We just made it evolvable. And then another goal, of course, is to have fun. And we love challenges. So our meta goal is the three virtues of a computer programmer are laziness, intelligence, and hubris. I learned a lot about impatience on drive over here. You guys drive funny. But as a community, we also encourage the corresponding goals of diligence, endurance, and humility. And so we use them where they're useful. And along the way, in addition to just fixing the things that were bad or good about Perl 5, we had some really cool stuff. So what does Perl design mean? Well, there's one way to do it. He did things easy, hard things to be possible. All fair to be declared. Blah, blah, blah. Blah, 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 blah. No arbitrary limits has been in Perl from the beginning. But what I really would like to do is show, I'd like to actually show some code, because I think that will be much better than me talking about it. So, did I put that? With all my time? I want to wander over here. And I don't think this. Adaptability is important. Pardon me for sitting here. You saw this code earlier. It's in that forest program that I was running at the beginning. What are some of the things that we've added in Perl 6? Well, first of all, you notice we actually have a class declaration. You can do classes in Perl 5, out how you wanted to do it yourself. So, of course, everyone designs 20 or 30 different ways of doing it. In Perl 6, there's still the same flexibility underneath, but we provide a single default. That is the normal way of doing classes. It looks very Java-like, except in the ways that it doesn't. So, we have things. We basically added more declarators that really run code underneath and do the things. So you still have the flexibility of running code, but the declarators look like they are happening in compile time, because they really are. You're just running code in compile time. So we can declare enumerations like here, I think this might actually work better. I'm going to steal this. Yeah. Okay. Now if I don't have a piano on instead. So there's a new method here. The only reason we're defining a new method is because we want to have a custom new method, but you get one by default as long as you're willing to use named parameters. The attributes in a class have what we call a quidgel after the sigil, which tells you the scoping of it. Normal variables don't need that. They just have the sigil, which tells you the data structure if you're not familiar with that. So it's kind of a little tiny Hungarian notation. In Perl 5, you can only loop over one variable. In Perl 6, you can say use this cross operator, which says take every combination of height, width, and then you feed that to a closure. It's a lambda, basically, if you're familiar with functional programming. And so we can now take things 2 at a time out of a list, or 3, or however many you want. Basically, general signature matching on whatever your input list is. And then we can iterate over that. So that's another thing. Here's another example of a 2-dimensional list here. Anyway, this program is what I was running earlier, which, if you saw it coming in, it was doing the forest fire simulation. And so we actually it's taken us 10 years to get the design to where we more or less want it, and we're starting to get several implementations. One of the things about Perl 6 is that we will have multiple implementations, and the language itself, instead of being defined by a single implementation, will be defined by the specification and by the test suite. And so we have a test suite. Oh, we've got a little tiny forest fire there. Currently, this particular implementation is the most correct and the most advanced, but it's also the slowest. So you see that this running the simulation at full speed, it's 3 or 4 orders of magnitude slower than what it eventually will be. Oh, there goes another forest fire. Poor forest. By the way, this is the Chinese character for tree. So, one of that. Okay. What else do we have here? We also have a command line. If you just say Perl 6 like this, you get a command line interpreter, a REPL, as we say. So we can, what would be a good thing to show here? We have another thing called meta operators is another concept, which we actually, if any of you have programmed an APL, it has meta operators, except in Perl 6, they're actually readable. So you can take any infix operator, for instance, and put square brackets around it, and it becomes a prefix operator. So if I say, add up the numbers from 1 to 10, comes up with 55. And basically what that says is take that plus and shove it between each of those numbers. So we call it a reduce operator. So
you know, lots of different computer languages here. There's this site called Rosetta Code. I keep calling it Risotto Code. It's Italian. Rosetta Code, like the Rosetta Stone. And they compare many different languages. So you can go in and see what it looks like for me here. Fix this. Yeah. Okay. I was going to show you factorial. That's what I was going to show you. So you can go to a page like this, and it shows for all these different languages how you write factorial. There's how you have to write it in Ada. Languages are very interesting to compare because, as a great linguist once said, languages don't differ in what you can say. They're all Turing complete, as we say. But they differ in what you have to say. And this was said about natural languages, but it's also true of any Turing complete language. The idea of a Turing complete language is powerful enough to write to solve any problem, any computable problem. So here's C, because there's different ways of doing this. So we can actually, if we go down to there'll be an entry in here for Perl and Perl 6. So we go down here, we have, oh gee, that doesn't look like anybody else's. What are we doing? So if we're just using a operator like this, so factorial, 10 factorial is that. And we're just multiplying those numbers together. So we don't have to have specially named functions for most of these things. Anything you can construct easily. That x that you saw earlier, which was we call a cross operator, which does basically the cross product of all those things. That also can be used as a meta operator with other operators. So suppose I have two lists. If I say A, B, C, cross concatenate with 1, 2, and print that out, you see we get every combination of A, B, C, and 1 and 2, and concatenated together as a string. So this is a very powerful way to extend operators. And I talked about visual metaphors. You notice this is uppercase. That's because it is actually a list operator. It controls two lists on the other side, on each side. So as a very low precedence operator, you want to be very big so you can see it easily. Likewise, we have a series generator operator, ... So I can say 1, comma 1, then add whatever to whatever. That's a function which says how to get the next value, given the previous two values. ... That's a list operator. And just go however far you want. This is the Fibonacci sequence, which most computer texts will define recursively, but that's kind of a silly way to do it. And we can say, well, just print out the first 20 of those. And there's your Fibonacci sequence. So there's a lot of power in what we're able to do here. There's also much more extensive parsing capabilities. How are we doing on time here? Okay. This is the standard Perl grammar. It is written in Perl 6. So many of you have used regular expressions in your programming, if you've done that sort of programming. And they pattern match on strings. Well, parsing is really just a sort of higher level pattern matching on strings. So we've extended these regular expressions to be much more powerful, and now they are actually grammars. But you still use things like the star, which says 0 or more times. And you still have character classes here. It's A to Z. They're written a little differently. But we basically redesigned everything. The vertical bar here still means this or that. And it's just a very powerful way to get things done. Do I have any other... let's finish up with the turtle. The turtle is a lot of fun. Okay, in fact, it's also out here on the Rosetta code. It's here as there's a zigzag matrix and there's a spiral matrix. Yeah, there. And so you have, the idea here is that you're going to produce a matrix where the numbers spiral around. And when you think about it, you can do that two different ways. You can go from the outside in or from the inside out. So I've got a little thing here that does it, and it does it using turtle graphics. Okay, again, we have an enum here, which is our cardinal directions. This is very stupid turtle graphics. So those of you who are into fancy robotics, squint a little. This is a very dumb robot. It can only go one of 8 different directions here. And so we have a class that's turtle, and it basically knows about its world that it's crawling around in. And it has a turn left method, and a turn right method, and a lay egg method. And it can look ahead of itself, and it can go forward. And that's all it can do. It can also show what it knows about the world that it can show where it has laid eggs, basically. And so now we have a main subroutine, which will actually do the matrix here. So we have a loop. Okay, and so we start the turtle facing east, and we move forward, and then depending on the size of the matrix that we want, we go around in circles and we keep reducing. This is a reverse list, so the runs get shorter and shorter as you're going in the spiral. Okay, well, let me show you what it does. Let's see, they had a 5. So we can make a spiral matrix. Let's make one that's a little bigger here. You see, it actually redraws the screen and it figures out when it gets above 100, it will actually shift over again. It's a little clever algorithm that way. Now, what I've written here, you might have seen that said multi-main. Many of you know about main routines in a program like, in a language like C. You have a main subroutine that gets called when you do it. Well, Perl 6 has a very powerful signature matching, which means you can have multiple functions with different signatures, but they have the same name. This is usually called multi-method dispatch. Perl supports that generally, but a specific instance of that happens to be that your main subroutine can be a multi-method too. So we're matching the signature, and it automatically parses the command line for us. So we know that if the first word is this, and there's a size, then we do this algorithm. But if the first word is this, then we'll do this algorithm, and if the first word is that, we'll do a zigzag algorithm. So here's the Audi one, turtle, Audi, and this builds it from the inside out instead of the outside in, which is kind of cute. Now the zigzag matrix, if you remember the description here, Oh, you didn't see the description because I didn't show it to you. I am silly. Anyway, it just goes zigzags back and forth on a diagonal. And it goes like this. Turtle. Now the interesting thing about this is you can actually see it pause at points and do garbage collection. The garbage collector in Rakudo Perl 6 is still kind of slow. They're going to replace it with a generational garbage collector soon. So it's kind of fun to watch this turtle crawling around its little world. Well, I'm basically out of time, so... So I basically like to leave you with this picture. Many of you are in engineering, and many times the whole point of engineering is to get a solution which is just good enough. You don't have to have a perfect solution. As you live your life, you will find yourself many times in a position where everyone is telling you, "Oh, just stay there. That's the right way to do it." But keep thinking. Sometimes you want to get to a better place. So, and if you do get to that better place, many other people will be happy with what you do. And it won't make everybody happy, but if my experience is any guide,